Hey guys, it's Team The Sudors. This is our Assignment 3 presentation. In this presentation, we will talk about first, architecture design and changes, second, quality attribute comparison, third, third-party libraries and services mapped to main components, fourth, front-end subsystem overview, fifth, our prototype point 1, and finally, conclusion and lesson learned. We are mainly using the MVC architecture style for our chatbot service. This aligns with our conceptual architecture design. The MVC architecture style divides our project into 3 components, which are model, view, and controller. The model manages all the data and business logic and contains the heart and soul of the service. The view displays information to the end users, which is received from the model. Lastly, the controller handles input from the users and manipulates data within the model. We have added concepts of the SOA design as well to our current system, which expands on our conceptual architecture. SOA is important in our design phase because one con of the MVC pattern is that the model is responsible for doing all the work. As such, there can be times when work needs to be done in parallel, and having one model do everything would cause overall performance hindrance. Thus, SOA was brought into the equation to have separate component, which helps break the model up into certain pieces, so the overall performance is not directly affected. In our case, users from the view component request the model to display a list of items by a product keyword. This is done by the controller sending a request to the model that handles the searching through the internal products database, if matching products exist, or it tries to scrape data from commercial providers if it does not. The model handles the business logic and determines what needs to be done after the request from the controller has been made. Then, after the model computes the request, the information is relayed back to the user using the view, which renders the items list through our websites. In conclusion, the model handles data processing, the view deals with presentation, and the controller tells the view and model what to do. With that said, the model incorporates SOA concept, namely in the gathering of items to return and adding items to the database, which is handled by a REST API that is used to communicate between the front-end and back-end subsystems. The ISP also plays a crucial role in triggering the web scraper and thus is responsible for that too. Supporting concurrency is a major requirement for any database system that needs to handle requests from many thousands of users. MongoDB allows multiple clients to read and write the same data. In order to ensure consistency, it uses logging and other concurrency control measures to prevent multiple clients from modifying the same piece of data simultaneously. MongoDB uses reader-writer lock that allows concurrent readers shared access to a resource, such as database or collection.
Here we have some performance and scalability requirements. We want to make sure that the application returns a message within a given amount of time. In order to achieve that, we would increase available resources for the database and use more efficient implementation of the scraper. We also want to make sure the database can hold enough information without affecting its overall performance, so we would increase the resource capacity for the database. We set hourly check for item price drops so that we can send a message within an hour to users who signed up for the notification. We will increase resource capacity during the product updating time so that it doesn't take more than 30 minutes. And then the portability, compatibility, and usability requirements. During the development cycles, we would test with different browsers on different platforms and make sure our app is compatible with most browsers, platforms, and operating systems. In order to increase the accessibility of our application, we would comply to the WCAG or the Web Content Accessibility Guidelines. And also, we would like to test our app with different users, collect their feedbacks, and improve the learning curve of our application. For security requirements, of course, we want to make sure the user's information are not leaked or tampered. We would create form entities that are securely escaped and use HTTPS protocol for additional security. Finally, we want to maximize the availability and minimize the maintenance time of our application. By pinging the service periodically, we can detect any crash and escalate a restart immediately. And by proper planning, we can reduce the maintenance time.
Our system uses various third-party libraries and services mapped to main components. The Chatbot service uses JavaScript-based frameworks, notably Vue.js and Node.js, to power the front end and back end of the service respectively. Alongside that, the service contains 4 main components, which are broken into the Chatbot interface, the database, the web scraper, and the backend database API. Our Chatbot interface takes requests from the users, allowing the users to interact with the system. The main user interface is built with the Vue framework. The bot, through Amazon Lex service, takes the messages and tries to determine the intent of the user and the context of the conversation to deliver responses based on what we've provided as options. Once the bot confirms the items that the users are looking for, the system will search through our database to find the cheapest products. The findings will be displayed to the users for their consideration. We also employed Amazon Cognito and AWS Amplify for user authentication. MongoDB is our database of choice, as MongoDB is used as a cloud database that runs on MongoDB's Atlas service. It is our choice of database because the database structure uses a NoSQL database style, which tends to have many pros over an SQL database, such as flexible data models and fast queries, which are perfect for the chatbot because we are having to scrape from many different websites, which allow us to retrieve different types of data amongst the different types of websites. Thus, NoSQL would be a better approach. For our web scraping, we use web scraping techniques to extract existing data from selected shopping websites such as Amazon US. The web scraping identifies HTML data and processes them into data format that can be easily stored. In our case, it's a JSON format. The web scraping is written in Python and uses this library Beautiful Soup designed for web scraping and is utilized to extract item information. The return data will then be displayed through our chatbot interface to the users. For our backend API, the chatbot uses the Node.js framework to power a REST API which connects to the database and returns the database results based on the given queries. This backend API is meant to be kept internal and only used for the chatbot service to query the results and pass to the AWS Lex instance. This is done by using AWS Lambda functions as they are perfect for quick executions, which means it's perfect for our chatbot. Alongside being able to return results using GET requests, the API also supports post, delete, update requests for adding additional products to the database, deleting products from the database, and updating product information to the database respectively. Lastly, the chatbot service is using Docker to deploy containers that hold the front-end and back-end services respectively. Docker is a container technology that allows us as devs to create images of our front end and back end, which promotes portability of our service. As our service gets more known, there are chances for system crashes or load balancing issues down the road. In instances such as those, Docker would be very helpful as we can start up a container faster than a VM or a new server, thus allowing us to keep the uptime relatively high.
The front end has a chatbot interface that's connected to AWS LexBot using JavaScript displays responses based on users' input. The front-end subsystem also has authentication features integrated through AWS Amplify, which interacts with AWS LexBot through JavaScript. This diagram shows all use cases we plan to implement. The green use cases are our main focus at the current stage of the chatbot system development. The chatbot's primary functionality is that users can search for items, and the chatbot returns a list of items with their price and images. Search for item is available for both anonymous users and authenticated users. Authenticated users will access services such as viewing history and setting price alert, etc. As shown in the sequence diagram, the chatbot server handles the user input, parses it and sends it to the database server. The database then queries the data, finds the proper results, and displays the results by passing them back to the chatbot server. If there is no matching data found in the database, the system will scrape the data from Amazon and add them to the database. The deployment diagram shows that chatbot front-end and back-end run in Docker containers, and the Docker containers run locally on an Amazon EC2 instance. The UI acts as a view and controller in our MVC design, as this sends user input messages through HTTP protocol to the AWS Lux instance. AWS Lux applies the Lambda functions in the backend, which then communicates with the backend API through HTTP protocol. The API interacts with Mongo database or web scraper to retrieve and return data. In the class diagram, the main.js and app.view classes act as a model which do most of the computing and the initialization of components to be seen on the view. The routes.js class acts as a controller as it does the routing between the view and the model. The rest of the file that includes about view, sign out view, home view, login view, and bot view act as the views as they represent the information to the end users.
The first prototype for the chatbot consists of some important features but does not display all planned features which are to come. The two features that we will show are the use cases mentioned previously. The first use case being that the user can search for items through the chatbot, and the secondary use case is user authentication. As this is the first prototype, the chatbot does not have functionality to compare items within different platforms and only works to show item prices from Amazon. A screenshot of the first use case is shown here, which shows how an end user will typically communicate with the chatbot. The chatbot welcomes a user to the service. As shown in the screenshot, the user messages are in purple and the bot messages are in blue. As the user is not logged in this case, the chatbot greets the user and tells them to sign in for custom features, which are again planned for later releases. The user then tells the chatbot that they'd like to find an item. The chatbot identifies the user intent and responds to them asking what they're looking for. The user then inputs the item name. The chatbot then takes a keyword from the user and searches the database. Since nothing was found in the database in this case, the chatbot returns that no results were found. At the same time, a web scraping action is started where data for these keywords is scraped from Amazon. The next time the user searches for the same item, the chatbot then displays the results to the user as the web scraper action was successful in gathering data from the previous command. This can be seen in the screenshot. For items that already exist in the database though, the chatbot quickly responds and returns those items to the end user instead of showing no results found message. The second use case that we'd like to show, which is just a preview as of now, is the authentication. This will allow users to have extra features, including favoriting items and setting price alerts once they're implemented. As of now, for authentication, the user can create an account, log in, or reset their password. As we weren't able to showcase all the different chat options within the chatbot, we have provided here a link to the chatbot service itself for anyone to play with. As it's just a prototype and not a complete product yet, the features are fairly limited, but hopefully it gives you an idea of what to expect from a future release. Overall, after the implementation phase, our architectural design did not change from our conceptual architectural design as much, with one exception of us using some concept of the service-oriented architectural design to divide our model from our MVC design into different pieces so that we can have work done in parallel. In the end, our first prototype had different subsystems in the front end, the back end, and other components that work together to create our chatbot. Working through this phase of the project, we realized that it is difficult to analyze and report the concrete architecture of a system because we learned that the concrete architecture has more dependencies and thus does require some changes to be made from the conceptual architecture. This can be attributed to the conceptual architecture not being able to directly be converted into a concrete architecture due to the underlying behaviors that come up during the implementation phase. Thank you for watching. Please leave any questions below.